Hello, welcome to Cosmology Talks. This video is the first in a whole series on CAMELS, who are a group who are trying to apply machine learning to cosmology with a whole suite of simulations from which the machine can learn from. So this video today is the intro. It's a super brief intro into CAMELS and the data release, so how you can use the data for your own purposes, machine learning or otherwise. This video features one of the CAMELS PIs, Paco Villanueva. There will be a live discussion in Feb or March of all of these videos about all of the cosmology. So if you have questions and want to come to that live discussion, let me know and I can put you on the mailing list. I'll be dropping a new video every day until all 8 of these videos about CAMELS are out. This video is only covering CAMELS in general and the data release. The other ones will be talking about individual research that has been done using this suite of simulations and using machine learning. So if you want the cosmology, watch those ones. If you want to have the background, watch this one. Other than that, enjoy. Welcome to Cosmology Talks, Paco. Do you want to start by telling us briefly what it is that CAMELS is?
So thank you, Sean. So CAMELS is a project where basically we are trying to create connections or try to build bridges between cosmology and astrophysics, or more in particular, let's say, galaxy formation. And basically the way to do this is to use numerical simulation, state-of-the-art hydrodynamical simulations. Many of them, not only one, like thousands of them. So we can really, prove different cosmologies, different, let's say, galaxy formation models. And basically the glue to put all these things together is machine learning.
Oh, and so what is it that you wanted to do with CAMELS through this machine learning that normal cosmology can't just do anyway? Because I imagine you want to enter a new paradigm where machine learning is seen by everyone as normal cosmology.
Basically, CAMELS come from, is not that it appears out of the blue. Many people has been, in the recent years, seeing how much information there is in the cosmic web. Cosmology, typically we use the power spectrum when we do, let's say, galaxy clustering. And on small scales, we know that the power spectrum is not able to fully characterize the cosmic web. And basically, we don't even know how much information is there. So basically, the main idea behind CAMELS, for applied to cosmology, is to look at the cosmic web on very, very small scales, or smaller scales than what usually people has done before. And let's see how much information there is about cosmology on these scales. The thing is that, of course, this is the regime where we need to worry about astrophysical effects, supernova feedback, AN feedback. So in principle, you would like to take into account these things. So that's basically what in CAMELS. So answering your question, Sean, we basically want to look at how much information there is in the cosmic web, not to, let's say, k of 0.2, let's say 0.5. We want to go all the way to k of 30. We have already gone to k of 30. There is information there. And maybe in another video, we will see how much information is of k 500, when you go to a single galaxy.
Cool. Do you want to get into the details about specifically, like, what are the simulations that you've done with what algorithms?
Basically, in CAMELS, we have like more than 4,000 simulations. Half of them are traditional embodied, nothing maybe in particular. The other half are state-of-the-art hydrodynamical simulations. It's very important, I think, to don't rely on a single code, because there are different codes that solve the hydrodynamical equations in different ways. And also, the ways that we model the formation of a star, the explosion of a supernova, and these kind of things depend from code to code, from group to group, from model to model. So that's why, in our hydrodynamical simulation, we basically run the simulation using 2 completely different codes, the AREPO code and the Gizmo code. And the subgrid physics, these recipes for the way that we form stars, the energy released by supermassive black holes, they are also implemented using 2 completely different models. One of them is the famous Illustris TNG, and the other one is, of course, the famous SIMBA simulation. So basically, we took these 2 simulations, and what we do is to run a lot of simulations varying the parameters of them. So we have 6 parameters that we vary in CAMELS. 2 are cosmological, omega matter and sigma 8, and the other 4 are astrophysical parameters. 2 of them control basically the efficiency of supernova feedback, and the other 2 control the efficiency of AN feedback. And the idea here is to vary this within a crazy range. There is a lot of simulation in CAMELS that are not realistic at all. Galaxies are very strange there. And this is maybe because, maybe in this case, AN feedback was too large that you don't really produce a realistic galaxies. But that's okay, because, at the end of the day, we want to basically use machine learning such as you can really explore the whole parameter space. The idea is that you run maybe 1,000 simulations, you explore the parameter space, and then a neural network or something like that can maybe explore the whole parameter space. And then once you are able to explore the whole parameter space, you can really compare with real data or do whatever.
Yeah. So whatever physics it's discovering is kind of robust. It's not overfitting some narrow range with some algorithm that isn't like a physical algorithm. One thing that I think might be a little confusing is when other people have been talking about the work within CAMELS, they use the words illustrious TNG and Simba quite freely. There's the illustrious TNG collaboration who have built simulations like illustrious TNG 300 and such. That wasn't you guys at CAMELS. That was them with their big simulation. And then you used the code that they used and reran your own simulations. So I guess just the distinction will be when people are probably saying CAMELS illustrious, they mean the specific new simulations that were done. But then sometimes people have kind of tested against the actual illustrious TNG 300, for example, I think. So just be aware of that, viewers, that there's illustrious TNG's own simulation and then there's illustrious TNG code CAMELS simulation. People maybe aren't making it super clear which one they're talking about when they're talking.
You're completely right, Sean. I mean, basically, we wanted to leave the name because we haven't really touched anything in this code. So all the credit for this simulation should go to the illustrious TNG team or the Simba team.
Do you want to talk us through how to access this data now that we can use it ourselves and discover whatever secrets you haven't already found?
So basically, the way to download the data is to go to the website, and here we have some documentation. So you can you see this, Sean?
I can. I can't see the URL at the top. So if you just tell us, maybe if you just Google CAMELS Cosmology, you'll find this webpage. But do you want to just state the URL for people who are listening?
Yeah, so it's camels/simulations.org. You can go to here documentation, and it's going to bring you to a different website where we have a little bit more of the technical details. So there is a lot of, I mean, for everything is kind of explained here. The only thing that maybe it will be interesting is how to really access the data. So you can go here to data access. So this is basically like the technical documentation for how to work with CAMELS data. And if you go here to data access, there is like all the possible ways to work or download the data. So for instance, we have the globus. So, if you want to just move the data to your own machine or your own cluster, so you can just click here and, this is going to bring you directly to the page where you can download the data using globus. You can just take, the traditional URL link, like the one here, where you have this with the browser, and here, you can just download the data clicking or using something like wget or these kind of things. The only thing that I want to emphasize is that we also provide this binder, who is basically a way for you, to even work locally with the data. It's not really designed to do heavy calculations, but you can really work with the data, manipulate, do some kind of simple calculation that don't require like massive amount of time. So if you go there, you click, and then you will just be able to access. You need to here authorize this.
I guess the main point, from your perspective at least, of CAMELS is the machine learning stuff. Is there any machine learning-y tutorial-y things that people can learn how to not just download the data but investigate it?
Yes, definitely. I mean, this is kind of a little bit designed to do this. For instance, this is a way to quickly maybe take a look at the data, to see if things make sense. And we, of course, have, for other papers, we have a lot of, like the actual code that we use to train the networks.
And that code is public on that webpage as well?
So usually, this is associated to the paper. If there is a paper doing this particular task, usually we put the GitHub link where you can go and you see the code that it was used for this particular thing. Okay, so here, for instance, you can, like a normal terminal. So you can go, for instance, here to the data, and you see here there are all the different things. So you can, go to the simulations that are called scenes. And here we have, the illustrious TNG simulations, the dark matter counterpart of the illustrious TNG, the Simba. So you can go to illustrious TNG, and there is a lot of like more than 1,000 different simulations here.
Can you maybe just super quickly distinguish between 1P, CV, and LH? Because I know some of the other speakers were freely using those letters without defining them.
Our suite is illustrious TNG or Simba, which is kind of like the completely different simulation model or code that you use to run. And then there are 4 different sets. So one of them is called the LH, that is Latin hypercube. And basically, in this case, there are like 1,000 simulations that are arranged in a Latin hypercube. So this is like most of the data is in this LH set.
What is a Latin hypercube?
So a Latin hypercube is basically, imagine that you want to sample the parameter space. There are different ways to explore the parameter space. The simplest one is to take like a regular grid, and you just take a point in every point in the grid. So this Latin hypercube is basically that you take like a regular grid,
like a 6-dimensional grid of all of the parameters.
but you only put like let's say 1 point per row and per column. In a regular grid, you are putting basically in all the rows and in all the columns, you have a point. In a Latin hypercube, you only put like 1 point per row and per column in every dimension. And basically, it has been shown that this is a much better way to sample the parameter space. And then we have, this CV set that is basically, 27 simulations with the same cosmology and astrophysics, just different random seed. This is sometimes you want to quantify how important is cosmic variance. The 1P set is basically a simulation where you only vary one parameter at a time. That's what 1P, from one parameter. And it's like, what happens when you only vary AGN feedback? So with these simulations, you can try to address these questions.
And I guess EX is the last one.
And ES is a string set that basically was designed like, this is like what will happen even with the craziest model that you can ever imagine.
Do you have any where you've got the same seed varying parameters? Because you said you had same parameters varying seed.
Exactly. So same parameters, different seed is the CV set, but same seed and different parameters is the 1P set. And this is like another different way. You can also, in this binder, you can open like a Jupyter notebook, and here you can really work with the data itself. So for instance, you can load the data, the typical things that we do, and you can maybe read a snapshot. So let's say a snapshot is located in data, scenes, maybe Simba, and then LH7, and then I think maybe we take the snapshot at redshift 0. So this is how you just define where the snapshot is, and then you can open it.
Okay, just super stupid question. Are you doing this on your own computer or on the Flatiron server?
This is in the Flatiron server.
Another cosmologist can do this as well. That was what your point was.
Anyone in the world, exactly. I mean, the good thing about this is that, there might be some people who maybe don't have, 300 terabytes to store all the data, right? But they maybe want to take a look to see if the idea that they have might work or not. So these kind of things might be like very good because, you don't really have to download the data. You can work here directly with it. And if it works, then maybe you can figure out how to do this.
Or perhaps get in touch with you guys and say, we've got this great idea.
Definitely. This is one particular simulation from the Simba simulation. This is a snapshot at redshift 0. And let's say that you want to read the position of the star particles that we have there. So you will do something like, in this case, will be particle type 4, because these are stars. And you will do this. And then you can maybe just close if you have finished. And that's it. And you can here take a look at the position of the stars. Just like that. You can manipulate all the data. You can read the snapshot. You can read all the other data products that we have, galaxy catalogs, Pau spectra, bispectra, Lyman alpha, quasar spectra, So this is a little bit, what the things that we have done until now. I think Lucia has been already talking about how to expand CAMELS using this very large suite of embodied simulations that are combined with the Santa Cruz semitic models, so we can go to even larger volumes. Jay, Leander, and Emily has been working on things that are related to the THC, KHC, also with galaxy clusters.
We had Jay and Leander, but Emily was busy. But if you're super keen for a talk by Emily, let me know and I can find a time. Yes,
and Andrina has been presenting her work that looking at how robust we can do maybe cosmology and astrophysics when we look at the, let's say, properties of the intergalactic medium with electron density and these kind of things. And then, Faisan and Sultan has been working a little bit more at the level of the maps.
So Sultan we heard from, Faisan we didn't.
And then, Helen, that I think you already shown, has a full video with her presenting these universal relations. And then Pablo Villanueva, who also, I think, make a video showing how to weight the mass of dark matter halos. And yeah, basically this is a little bit what the different directions that we have following CAMELS.
So if you don't have anything else to say, the next thing on the list was where to next for the CAMELS team.
So for the next thing, I think it's important to realize what are the limitations of CAMELS. So the limitation are the volume is small. These are only 25 megapascal boxes. Even if probably we have sampled the largest volume in parameter space ever simulated, this is still not large enough. The volume in parameter space is still much larger than the one that we have sampled in CAMELS. And also, is that we only have two different codes right now. We have Arepo and Gizmo with the Illustrious CNG and Simba. It will be great to have more. So basically, these are the directions. So the small volume basically is that we don't have a lot of clusters in the simulations, and we don't have big voids. So it will be great to design simulations where we are able to prove this thing with something like zoom-ins. And then, in CAMELS we only vary omega matter and sigma, but there is more parameters, right? There is H, there is NS, there is W, there is omega baryon.
There's beyond lambda CDM as well.
And there is, of course, beyond CDM, W, not. So, ideally you would like to explore this, but also, for the astrophysics, that parameter space is even larger. In CAMELS we vary 4 parameters, but for instance, for something like Illustrious CNG, there are of the order of 30 parameters. We took these ones because we thought that these would be the most important ones for cosmological observables, the one that will produce the larger effect. But, if we start going at the level of individual galaxies and all these things, we need to vary many more.
Yeah, and if you want to match the real world, say actual predictions and make actual measurements, then I think the real world hasn't only varied those parameters. Well, actually, it's chosen one value of all of the parameters, but we don't know what that value is.
Exactly. And, finally, the simulation, we are already increasing CAMELS and there will be many more codes. So it's going to be really great.
Awesome. So hopefully everyone's very keen and is about to go and watch all of the other talks on what great stuff CAMELS has done. And presuming that after that they're still in love with all things CAMELS, how do they get involved?
So it's maybe a little bit strange that I say it, but there is a lot of low-hanging fruits right now with this kind of data. So, CAMELS is right now becoming a big collaboration. I will say there are tens of people involved on it, and there are people who are pure cosmologists, some people that are coming from galaxy formation, who are more into that side. There are maybe some people that are much more familiar with machine learning, but we all are kind of working together, so it's a very, very nice environment. So I really suggest everybody, if you are curious about or have any ideas, please reach out and join the CAMELS thing. So feel free to send an email to contact any of us.
Is there scope for people who aren't astrophysicists or cosmologists at all, but might be like experts in machine learning algorithms to get in touch?
Definitely. We are facing some problems that I believe are not only a problem for cosmology. These are very generic problems for machine learning. So they will be super welcome. And
it does seem like having a huge suite of simulated data is a kind of machine learning enthusiast's dream playground almost.
Exactly.
Yeah. Awesome. Cool. Well, thanks you and the CAMELS team for all the great work and all the great talks.
Thank you.
So that's CAMELS, the data and how to use it. Now go watch some of the videos about the work being done by CAMELS. There's a playlist in the description if you want to watch through the playlist, or click the video that's being suggested on the screen in a second. If you want a more depth intro to CAMELS, you can go watch the other video being suggested at the moment, which is from the Cosmology from Home conference. And like and subscribe if you want more cosmology goodness in your life. If you like and interact with videos like this, YouTube will suggest more videos like this.